So I hope my screen is visible and I am audible, right?
Yes, sir.
Okay. So we'll just wait for maybe 2 more minutes and then start, okay? Because no one has joined and we need some more persons and then we can start, right? So meanwhile, if you have any doubt in the previous weeks or in this week, you can just ask me. And I just encourage you all to join maybe sometime before. Like we do every Tuesday, 7 to 9. So you guys can join maybe 10 minutes before and just ask your doubts in the channel also or in the groups also. The Teams channel or group, whatever you call, and the WhatsApp. I'm not getting any doubts. So either everything is going very well or nothing is going well. Maybe something out of the two. Because we are not getting any doubts. So are you guys able to solve all the problems? Just want to ask. Or you are having some doubts and not able to solve. Just let us know, okay? If you have any doubts, you can just unmute at any time between the classes or in the group also and just ask your doubt freely, right? And if you are able to solve, then it is okay. Yes, so you can let me know anytime, right? When you are having doubt in any concept or problem related to a particular concept, you are having problem in implementing that concept. So you can just ask, we can just again go through that and then hopefully those the kind of problems you will be able to solve in the future, right? So that was what I wanted to tell you, because every week we are jumping into new concepts. So you should not forget the older ones because this is a very fundamental topic and all the concepts that we are going through will be required in one or the other way in all the sessions. So don't think like we don't need one concept and then you can jump onto the other concept, right? So all concepts are very important and whatever process are being taught are very quick process that will help you to solve in the fastest way. And also concepts are being taught that why such processes work, right? So kindly see the recordings and the class lectures and I think you will not have any problem, right? So we are going, not wasting any further time. If you have no doubts, then we'll just jump into week 3. And today's week covers the lectures. I hope you have seen week 3 lectures. Those are on AC circuits, right? Single phase AC circuits. And we'll solve and look into how to analyze such AC because up to this time you were dealing with DC. So we saw that how to deal with DC circuits and maybe involving inductor and capacitor and all linear elements and transients, how to deal with transients. So both steady state and transient analysis of DC circuits involving R, L and C are being covered. And we saw many theorems also, how to deal with such circuits. So now we'll just go into AC. So coming to the week 3, what we do, we deal with single phase AC circuits. So nothing about the system changes, only the excitation source changes. So we had a system, I told you, linear time invariant system formed of R, L and C. And we were exciting the system till now with DC. And that DC may be, and we are seeing the circuit behavior of the response. So DC excitation was being provided and we were analyzing this Y of t, either voltage or current. Maybe it's transient behavior or steady state behavior or both. So till now we were doing this. So now we changed this excitation to AC, single phase AC, and saw how the excitation, how the response gets changed. But now you need to understand that once we are dealing with AC, we are not dealing with one parameter, that is the strength of the DC. What you understand, the strength of the DC is being because DC is a 0 Hz signal, right? It is like this, that at t equal to 0, you have some strength, let's say 5, and I can write it as 5 u of t. That is from t equal to 0, onwards, when we start the time stopwatch, that is t equal to 0, because physically time equal to 0 is not defined. So when you start the watch, that is your t equal to 0. So when you start the watch, the strength is 5. And it is like simple, right? It is of amplitude 5 in DC. But AC is not so direct. When I say AC, it has two parameters, like in vector. When you studied in class 11 vectors, what you saw? A vector has two parameters. It is not a scalar, right? Scalar has only one, its strength or its value or its length, whatever you say, its weight or its density, volume, mass. But the vector is having some amplitude and the direction. So we denote the vector like, for example, x vector, and we see that the length of the vector denotes the strength of the vector, that is the amplitude or the magnitude of the vector, whatever you call. So magnitude of the vector, we say its amplitude or magnitude. And then we have another parameter, that is direction, right? So similarly, AC doesn't have any direction. So that's why we don't call AC signals to be vectors. We have some different name for it. You can call it phasor, right? So it has a phase. It has two parameters to deal with. So whenever you deal with AC, we have two parameters, right? One is amplitude and another is its phase. And these two parameters all depend on when you start the time, when you start the stopwatch. Because in nature, everything is cos, everything is sine. We say sinusoidal excitation. Now, whether it is cosinusoidal or sinusoidal depends on when you started the watch. Because one signal, if I start from here, it appears to be a sine. Because for my t equal to 0, it is sine. Now, if I start the watch here, it will be a cosine. So it depends all on the waveform as well as on the timing from which you started counting. So for that only, amplitude and phase can be irrespective of the time. But in AC, the amplitude varies with and also the phase. So both the amplitude and phase varies with time for AC signal. So both this signal needs to be taken care of, and both for the input and the output. So that is what I wanted to say. But can you tell me why AC instead of DC? You must have learned somewhere, or till now you must have some idea at least why we are interested in AC, why it came, and why it became so popular. You are using in the house, in the factories, everywhere you are using AC rather than DC. So just quickly, can anyone tell me why we are so much interested about AC, about analyzing the behavior of the system when excited with AC signals? So why maybe single phase AC? For this week, we are just limited to single phase AC. So why single phase AC? Can anyone tell me? Just unmute and feel free to become interactive, right? Because that will help. So till now you understood we are dealing with AC. And AC means the excitation is sinusoidal in nature. And it has two parameters, amplitude and phase. Amplitude means the peak amplitude of the AC, of the strength of the sinusoid, and its phase angle, which varies with time. Both amplitude and phase varies with time. Now you tell me why AC? Yes? I want some answers, right? Why are we so much interested in AC? Just feel free to unmute and become interactive, right? Later on, it will help you solve the problems. So why AC over DC? I can just frame the question like this. What is the most strong reason I can tell that you can think of? Because
The question.
the question is, what is the best possible reason that you can think of that why we are using AC in all our systems? Maybe
Because of transformers, sir, you will step up and step down the voltage.
Correct, but in DC also we can step up and step down using buck converter and boost converter. You must have, I think all of you are electrical engineering students, and by this time you must have heard about AC to DC conversion or DC to DC conversion. All are possible, right? AC to AC.
Fourier
You must
series
have,
analysis.
yes,
For
yes, I heard
math,
some term about Fourier series. Yes, I just, it's interesting. So who told Fourier series? Can just elaborate.
for mathematical analysis, for harmonic analysis, Fourier series analysis is very easy, sir, for applying for AC supply.
Correct. Fourier series analysis becomes very easy if, why he is telling like that, because what Fourier told, that any periodic signal can be broken down into sum of sinusoids. But why to go in Fourier series? That means why, but that is a mathematical justification you are giving. But why still the question boils down to, okay, that sinusoidal excitation or sinusoidal signal, dealing with them becomes easy because of Fourier transform and all the frequency response domain analysis. Frequency domain analysis becomes easy. You have learned in signals and systems that, okay, if my waveform is like this, then okay, I can analyze it well. But is it economic also? Because everything comes with the cost. If it is cheaper in practice, then we can deal with those signals. Mathematical analysis is difficult, okay, but who wants to pay more? So is there something related to economics? Because we are using it on our systems, right? And in the thermal power stations also we are generating AC rather than DC by burning so much coal and doing so much hard work, heating the water and then rotating the turbine, and then the turbine rotates the alternator shaft, and then the alternator generates the 50 hertz frequency AC, maybe of something 13.1 kV, and then the transformer steps it up, and then we are building such a long transmission line, and then it comes to your home as single phase. Because of the transformer, you can tell from the 3-phase you tap, one neutral, then 3-phase 4-wire system, and then one phase you utilize in your home. So then why so much interesting is the AC?
For low losses.
Yes, the losses actually becomes very low in AC. Why? Because why you know? Because the transmission line is having resistance, right? R. For the same transmission line, if you use a particular strength of DC, let's say 5, I am telling about the current 5 ampere. In DC, 5 ampere means flat 5 ampere. But in AC, the RMS value is 5 ampere, right? Because you know losses are I RMS square into R. Why so? We just see that power loss is I RMS square into R. So this is the average power loss is I RMS square into R. Why so? We'll just see the derivation. But just telling you that average power loss, it can be quantified as I RMS square into R. So what happens that the peak value of AC, even if it is 5 root 2, then the RMS value becomes what? 5 for a sinusoidal signal. And then what can you define about the power? VRMS into IRMS into, let's say, unity power factor, so 1. So voltage, let's say for the timing for both it is constant. Then can I push more power? Or for the same power, what advantage I am getting? I need to reduce this I. Because if this I reduces, the I, that is the current in this transmission line, if this reduces, then my losses can be reduced. So what I use, I insert, just someone told, I insert transformer. Transformer to what? To step up the transmission voltage, transmission line voltage. In the process, the I reduces because because of constant power theorem, right? Because if the voltage is increased, because in transformers you know, right? Because of MMF balance, if the voltage is stepped up, then the current reduces because the power needs to be constant, right? Other way around, you can also apply MMF balance. The current reduces means its RMS value reduces. So the voltage level goes up, current level goes down. So from 5, maybe it reduced to 1, but the voltage went up. But in transmission, the current plays the role because the loss is due to the current. So the transformer in AC are very much useful to reduce the losses, and the losses reduce only because of the transformer. And transformer will not work for pure DC. In switching, buck converter, boost converter, we do switching, right? So it is not a kind of flat DC, because if it is flat, then the transformer will not work. There needs to be some DIDT or DVDT across the windings to produce the rate of change of flux for the transformer to work, right? Otherwise, the transformer will just burn. So for that reason, the losses reduce. So one reason is losses reduce. What is the second reason? Mathematical analysis is easy.
Generation was in the form of alternating.
Yes. So what is the third reason?
Economical power transfer.
Economical power transfer. Correct. And in other way, the maximum power transfer capability of the system increases. Of system increases, right? Because my losses are reducing, so I can push more power.
Sir, I have one doubt, sir.
Yes, please.
For boost converter or buck converter output, transformer is working, sir.
Correct. We are not using transformer. Please just be cautious. There are two versions, isolated and non-isolated. So every kind of variants are there. Isolated converters, isolated DC-DC converters have transformers. They work on the principle of flux balancing, right? There also you have the changing flux because your currents are changing.
Works on which principle, sir?
Flux balance, you can balance the flux, right? The flux can be balanced. The flux cancellation is there, right?
Okay, sir. Thank you, sir.
So what happens? There is some flat portion that builds the flux, the DC value of current. So for phi there exists, for I there exists phi DC value of current, you can tell, average value of current. There exists some phi in the core. And then what happens? So that the flux don't increase, whatever portion, you can call it charging portion, the current increases, and then the next switching cycle, the current should reduce to reduce the amount of flux, because otherwise the core will saturate. So I can tell whatever is the increment in flux, that much flux should be reduced so that the core never saturates. But why I need the changing flux? For the working, because if you keep a flat current and a flat constant flux is there, the voltage will not change, right? Because d phi dt is required for the voltage to change. So you need always some kind of switching. Otherwise, what will happen? So what was your question? Just focusing on the question.
Okay, sir. Okay, sir.
Now, what was the question? I did not understand.
Sir, buck converter output is DC, sir.
Correct. Buck converter output is DC. This signal is also DC, na? See,
input
what we
input
call,
DC.
so yes, input output all DC. I am not bothered about DC or AC. I need some variation.
Yes, sir.
Right? Some switching action needs to be there. Otherwise, if there is no variation, you keep plugging on DC across a coil, what will happen? Can you tell me? Just simple question. Because one state will have such thing.
Out, sir.
Coil will burn out because current will rise and coil will burn out. Keeping in mind the other parameters don't change, but you know that the inductance also changes when the current varies. The inductance of the core also depends on the material. The material permeability also changes when the current changes. So everything changes. So inductance also reduces, and everything will be very, I think I can say, disastrous if you just keep on plugging a DC without switching. Everything will be very disastrous, right? And the main purpose will not be solved. So in DC, the game is completely different. And I just, because the discussion is very interesting, I want to also tell you one very good thing, that the inductor and transformer, can you tell me what is the difference? inductors and transformers. What is the main difference?
Inductor opposes the sudden change in currents.
Correct. But transformer is also, I can tell, coupled inductor. There is mutual coupling without considering the leakage. I will also deal with these kind of stuffs in the magnetic circuits in the later weeks, but just focusing on the concept, inductors and transformers. Inductor also takes a lot of DC current. I use inductor in the DC, just shown you. Inductors in buck boost converter are used. Also mutual coupling, coupled inductors are also used in buck boost converters. You must have seen if you learned some power electronics. Then there what happens? The flux is not like this. Whatever, just asking you, what is the waveform of flux in transformer? Transformer gets sinusoidal excitation in a power station, for example.
Yes, sir.
DC value or DC offset? No, transformer. I am telling you, in power station. Transformers in power station. What kind of excitation do they receive? Yes. Am I clear? The question is clear? I think we are facing some lag. Am I audible? Hello?
You are audible, sir. You are audible.
So I am telling transformer in power station, how the excitation is. Purely sinusoidal. So for that, if the voltage is purely sinusoidal, what is the flux?
Sinusoidal.
Purely sinusoidal. Small amount of flux is the build up, right? So it is also purely sinusoidal and it is dependent on d phi by dt, right? So V is d phi by dt. Yes, so flux is also purely sinusoidal in transformer. And whatever flux is coming additionally because of the armature reaction and all, flux is cancelling, but small amount of flux still remains in the core, right, to produce the excitation, right, or build up the medium for energy transfer. So we will go into those details later, electromagnetic coupling and all those. But just saying, the flux is also sinusoidal and without any DC offset. So this is fine. And I have not drawn correctly because you can understand if the voltage is like this, the flux will not be like this. There exists some shift, right? So the flux actually will lag. So right. So there is some shift, but flux will be sinusoidal. But for sinusoidal flux, there is no DC value in the flux. But in inductors are designed to operate at with some flux because you will push current. Inductors are always connected in series and there will be some current flowing that will create some flux, constant flux, because inductor will take some average current. On top of it, it will face ripples. In the buck boost converter, I am telling. So the core is designed in such a way, or you can tell the material is designed in such a way that it can hold some amount of flux, maybe 1.1 Tesla, if I consider the core, or maybe higher if you can take powdered core or some sandust core. So inductors are designed such that it can take some non-zero flux. But if you push more, just saying that you must have heard that inductors are designed with some. Are you aware why transformer there is no? What the role is played by air gap? You can increase the current taking ability by the inductor. How much current you can push to the inductor without saturating the. Audible?
Your audio and video both are lagging behind. Yes.
Okay, just wait. Just wait. Now is it clear?
Now okay.
Hello.
Now okay, sir.
Yes,
So
sir.
what I'm telling, inductors are always designed with some air gap. But transformer, there is no air gap. Why? Because inductor takes some current which has a non-zero average. So flux will also be non-zero in the core. So that's why if you increase the air gap, the permeability of the core will reduce. Am I audible till now?
Sir, yes, sir.
Yes,
So
sir.
permeability of the core reduces. That's why what will happen? You know the BH curve. So BH curve for a highly permeable material, the slope will be steeper. BH curve for a low permeable material, the slope will be further like this. So if the slope is further like this, for a particular amount of B, you see the current taking ability is more. H is Ni by L. L is the length. So you see if H increases, the current increases. The current taking ability increases without increasing the B. So that's why we generally put inductors with air gaps, but not in transformers, because transformers don't have to take non-zero operating flux, non-zero average, non-average. I can tell phi average is 0. So transformer average flux is always 0. So it doesn't bother about air gaps. It cannot saturate very easily because there is no one to saturate it. There is always the flux coming and then it has a negative cycle, right? But still the peak flux has to be taken care of and the core has to be designed of the appropriate dimension. So there are some design challenges also. But what I tell that there is some different set of challenges for DC and AC. And AC you have some different set of challenges. But in transformer and inductor will come again that what are its primary differences. Inductor is not an energy transfer device. It is an energy storing device because it has always to take some current continuously, non-zero average current. So the average current to the inductor will never be 0. In DC, I am telling, because it works both for DC and AC in power electronic circuits. But transformer, always the average current is 0, right? Because it is purely sinusoidal. And you know, over a cycle of the sinusoid, if you take the average, then it is 0. So transformer is an energy transfer device, right? Up to this, it is clear.
Yes, sir.
Whereas inductor is
Energy storing device.
yes, correct. Both inductor, capacitor, energy storing devices. Obviously, if you want to release the energy or the charge, in very crude term, we use the term charge. The inductor is charging or discharging. We used very frequently in the previous weeks. If you want to discharge the inductor, what you do? You just connect the resistor across it. It will discharge. Then again, you plug the source. It charge because the current increases linearly. So like that, we can charge and discharge the inductor and keep on filling its energy and releasing its energy. So they are energy, but not energy transfer devices, because in the process the energy is lost across some resistor. But in transformer, energy is not lost. Energy can be transferred, right? So there are some perspectives. And what is the next reason is that in AC, the main reason why we use AC is because our 3-phase AC machines are very fond. Yes. 3-phase AC machines like induction machine, synchronous machine are very fond of AC. That is space displaced current voltages, right? Space displaced 120 degrees space displaced balanced voltages, 3-phase voltages to create the rotating magnetic field. So we'll see it in the coming slides or the coming weeks that the 3-phase AC machines are very fond of balanced sinusoidal space phase displaced. I can tell balanced 3-phase AC because it will help it produce the RMF, rotating magnetic field. So that is also one of the reasons. And other reasons, maybe the losses are less and all those things. But one of the, again, very important property that will help you in many competitive exams, I can tell, is because of the linear time invariant system dealing with sinusoidal excitation. That is one of the property of the linear time invariant system. So if you excite a linear time invariant system with a sinusoidal signal, its output is also sinusoidal with the same frequency. So here you see, I have excited this linear time invariant system with sinusoidal excitation, an sine omega 1 t. So the output will also be bn sine omega 2 t, where I can guarantee that omega 1 equal to omega 2. because it is a linear time invariant system. You can see also the proof in Openham. Signals and systems. The proof is very easy, right? Signal and systems, Openham. So the frequency, what the property is that the frequency for linear time invariant system is unchanged if excited with a sinusoidal signal. Input, it is sinusoid, output will also be sinusoid. Now linear time invariant systems are all R, L and C element based networks that we are dealing with. So if we excite, always remember that if we excite maybe with 2 sin t, so frequency is 1. So the output, whatever voltage current I tell you to find out, always remember one thing, that its amplitude and phase may change. That is, it may be 2 times some x sine 1t plus minus 5. Some scaling or descaling may be there, or some phase shift may be there, but its frequency will be always same as that of the forcing function, that is the excitation. So omega 1 equal to omega 2, always true. And Bn, obviously there will be some phase shift, if you can write like this. So what will be Bn?
Sir, can I?
Hello.
Sir, why we are so interested to just get the same frequency, the omega 1 equal to omega 2 for this
Why
LTI?
we are in? Yes, why we are interested? One very practical justification is that if the frequency is not same and you design some AC circuit, okay, for example, you have some circuit, black box, you don't know what is there inside, and you excite it with some, for example, sine 1t. Okay, up to this it is clear.
Yes, clear.
Yes, and anyone may come and also excite it with sine 50t. Now this excitation is in hand of user or end customer or regulation company or the distribution company who sends you electricity. That is in their hand, right? Yes or no?
Yes,
Sir.
Yes. So now if the circuit, for example, your TV circuit or whatever circuit you use, just for the timing, I am modeling it with RL and C elements, right? Obviously, there is RL and C only and some diodes also. Now, if the frequency is changing, for example, the current becomes sine 50t and some current, maybe some 3. This is the current. So this amplitude also depends on the frequency. Why? You know, all the impedances, the XL and XCs, we call it reactances, they depend on frequency. Omega L and 1 by omega C. We'll see how this comes, omega L and 1 by omega C. So all these are frequency dependent. So if, for example, the current frequency is something different, say, for example, 100 times, then what will happen? The capacitive reactance or impedance will be 1 by 100 and it will start drawing more amount of current. So it will burn. It will just damage the devices, which doesn't occur in practical systems because you can never change the frequency in LTI systems. And also the diode based clipper clamper circuits and are there, all the 555 timer based circuits are there. They are also R and C are specifically chosen to maintain the frequency or to regulate the frequency, because these kind of R, L and C, not R, but L and C very much depend on frequency. L and C don't depend on frequency, but XL and XC depend on frequency. The reactance that these elements will provide, because whenever you excite a system with AC, the impedance, that there are 3-4 terms like impedance, Z. Whatever impedance, if this is V, how much current will it draw? That is basically V by I. V by Z, right?
By Z.
Yes. So these are all in phasor domain. I will just explain. But the strength of the current being drawn also depends on Z, and this Z is also depending on frequency. Because what is Z? Z is R plus J omega L minus J by omega C. I'll just tell you all these things. But these also depends on how much will they offer. Impedance also depends on frequency. So it is very important the frequency is well regulated. Otherwise, everything will just start blowing up in your home. If frequency goes out of regulation, within moment, everything will blow. Because there are capacitors. They will start drawing more current. For the same voltage, they will start drawing more current. Because now the capacitative admittance has reduced because of the increase in frequency. Getting my point, right?
Yes, sir. Got it.
Okay, sir.
Yes. So how much will be the strength of current being absorbed by individual R, L, and C elements? Not R, but L and C only. L and C elements. The strength of currents being drawn by L and C elements are very much dependent on, that is the strength 3 is very much dependent on frequency. Whose frequency? The excitation frequency. Because once you excite, the frequency will not change for LTI systems. But there will be phase shift and some scaling. How much scaling and how much phase shift? So you can just see the proof. I will just write the end result, that Bn, what you see here. So I am doing 1 to 1. See, I have written sigma. Sigma means a series of sign. So for one sign, maybe sine 1t, what will be the output? For example, there is sine 1t, okay? And I give the LTI system with this. So what will be the output? If I know the impulse response h of t, whose I can write h of s, I think all of you must know, Laplace. And if I replace s with j omega, then it becomes Fourier transformation. These are all signal system stuff, right? So if I take the Fourier transformation, it will be h of j omega, or some persons call it, because s equal to sigma plus j omega, this s. And if I plug in j omega, then we call it, without the real part, so this is the imaginary part, right? So then people call it Fourier transform. So if I know the impulse response h of t, I can just take the transform and find h of omega or h of j omega. And if I know the impulse response, then I can write what will be the output. Because you know that xt, which is the input, convolution with h of t will be nothing but y of t, which is the output. But a special feature comes into play, which is only holds for the sinusoidal excitation. So if I told you, if it is sinusoid, then one special feature is that you can write yt directly. And what will be yt? Yt, what will be it? If xt is a cos omega t, for just example, or sin omega t, omega is 1. So it will be what? A times multiplied with h of omega naught. Omega naught is 1 for this, or you may write omega. Omega is known, okay? Let it be 1. So mod of h of omega or h of j omega, cosine of omega t plus phi. Phi is nothing but angle of h of omega. If the excitation is cos omega t, a cos omega t, then output will be a times mod, that is amplitude of the Fourier transform of h of j omega, or someone write it as h of omega, and omega is known, okay? Omega is known, times whatever is here, cos of omega t, but with a phase shift. How much phase shift? It will be the Fourier transform of the impulse response at the value omega, which you are exciting. So this feature is very useful, and you can see the proof in open hand. I will just share the book in the group and post a link also in the YouTube channel, and also in the Teams channel. I have the book, so you can just see it. It is a very good book and a standard book for all competitive exams in signal systems, right? For GATE or for any exam, you see this book is the standard book, right? So this is the property why sinusoid is very important, and in communications also this property is very helpful in finding out what will be the output. And also just telling you one more thing, because if you find interesting, the Bode plot, what you see, anyone knows Bode plot and AC analysis? AC analysis, DC analysis, these terms anyone heard of? LT spice, someone used LT spice? or PSpice? Because in BTech projects, you will be using these things, PSCAD, PSpice, LTSpice. Anyone used such things? Yes.
So
Don't
we have
worry about
heard
the
about
time.
that.
Okay? Don't worry about time.
So
You'll have enough time.
we have heard about this application, but do not use that as application or any project
Okay,
in
you will
our
use in
course.
the future. Okay, because they are very useful tools, and for sure you will come across these things in the future. PSpice, LTPice, because they are helpful in doing the transient analysis. All the time you cannot do mathematics and find out transient analysis. You need simulation, right? For complicated circuits, how the transients will look like. It is very useful in power systems, power electronics. So for this, you use LTSpice, PSpice tools. Now, what these tools do?
So,
They take all the
so
things.
both these LT Spice or and these again different things. Both applications is actually free for us to use.
Yes, free, all free, all free. All free application, all student applications, right? Student versions are there, and LTSpice is completely free.
Okay, sir.
So
Okay.
these are very useful tools. And in AC analysis, what you do? Yes, please tell me.
That this is a software.
Yes, software to deal with complicated networks. Because all the time you don't do maths and find out ODs and then find out the solution to such ODs and do the transient analysis. Because for AC also there is transient. Likewise, in DC we do the transient. Similarly, for AC also there exists transient. The problems that we will solve will be of the steady state for this week. Single phase excitation, AC excitation, steady state behavior. Similarly, in the assignments also you are being given questions of the steady state. You are being asked that what will the steady state current, steady state AC voltage, steady state AC current of the single phase AC with RLC networks. We'll see how to solve this in the question. But there exists transient. So to solve or see such transients, the simulation tools are there. These are such simulation tools. These work with AC, DC, everything, or pulse waveforms or impulse waveforms, whatever you excite. It will be a simulation tool. Or MATLAB. MATLAB is also there. These are all simulation tools. So I encourage you to use simulation tools also to see whether your question and your answer matches. That is in the simulation as well as in the theory. You can use MATLAB, Simulink, PSpice, LTSpice, and you can just, there are inductors, resistors, you can just put the values and excite with the AC and just see over a cycle how your waveform looks like. And it will give you complete transient, and then you can see complete steady state behavior. So these are very interesting. And you can start learning and using these simulation tools. So what I was telling in the AC analysis. AC analysis is what? It helps to analyze the frequency response of an unknown LTI black box. There is a black box, there is a system. Always the system is not known, right? Likewise, in the problem I am giving you RL and C networks, you know what the system looks like. But for a complicated big network, for example, I am interested in a particular area, but I don't need to see the complete network. But I want to see the frequency response of that network. For different frequencies, what are the gains? Like for a filter, we'll see two-port networks. So we are interested in the filter. What response? If I excite it with a particular frequency signal, what is the response it will give me? So I am interested in the frequency response, not the complete system, but I want to extract the information of the complete system. In such scenarios, the AC analysis is very useful. That is what I'm trying to tell. Without knowing the network, without knowing how the R, L, and C are connected, this thing, I can just use some techniques and know the transfer function of this network. That technique is known as AC analysis. So what I do, I inject very small amplitude of sinusoidal signals of different frequencies. Let's say 1, 2, 3, 4, completely going up to megahertz. There are some AC analyzers, some instruments also. You can just search in the web. There are some AC analyzers also. For example, there is a PCB and you want to just do the AC analysis. In industry, they use this term, or the linear analysis. So there are several terms, AC analysis or linear analysis or small signal analysis. You just keep on injecting small strength of sinusoidal signals and keep on judging the phase shift and the scaling of amplitude. By using this property, what I told you, I can know the LTI frequency response. How? Because I see what is the phase shift and what is the gain. I can plot the Bode plot, and by plotting the Bode plot, I can get the frequency, amplitude, and phase plots. From there, I can derive the transfer function. You must have learned in control system how to derive the approximate transfer function of a system from a Bode plot, right? Up to this, what I am trying to tell you, is it clear that without knowing the circuit, how to know the circuit? By knowing the circuit from a control person's perspective, I mean only to know the pole and zeros and the transfer function. So if a transfer function of a LTI system is known, do you know the system? Yes, I can do the control analysis and I can design the controller for that. So AC analysis is very useful in such scenario with sinusoidal excitation. That is, it is a property, right? It can help you know a system if it is LTI system. So that's why AC analysis, piecewise linear analysis, they also tell, or small signal analysis, because in small signal term, everything is sinusoidal. Or even if you do that, see the Taylor's theorem also tells like that, that on small, in physics also you must have learned in simple harmonic motion that all very minute displacements or motions can be expressed as a simple harmonic motion. Simple harmonic motion means sinusoidal. All the signals can be thought of as sinusoidal. So these will be helpful in piecewise linear analysis. In real world, nothing is linear. In real world, nothing is linear. I can say LTI. But piecewise, for an operating point, piecewise, we can assume that it is linear. Its behavior is linear. So that's why this analysis is very important and very helpful in small applications, right? In a particular operating point. So now coming to the concept of lag and lead, right? So what you understand by lag and lead from an electrical engineer's perspective? Yes? Yes? Yes, please unmute and tell.
In the
Voltage-
sinusoidal,
For a
Yes.
sinusoidal signal, voltage
Correct.
waveform started. After some time, current wave is started. This is lag.
Okay. Lag. Now, whatever definition he is giving is correct, right? So he is actually, I can tell, assuming one thing. So for your convenience, I am trying to tell one thing, that these terms, lag and lead, they are all with respect to voltage for current waveform. In general terms, when nothing is specified and I tell you lag, lead, people tell the load is lagging, load is leading. What that means? That if you connect a voltage across such load, which I call it lagging load, then what it means, the voltage across the load and the current through the load, if I draw the phasor means the angle of voltage in a plane
Reference.
with its magnitude, keeping the reference as the voltage, and then the current is lagging. Means
Current lags voltage by an angle pi.
correct. So this is the thing. So lag, lead, how to deal? Basically, you have a time varying sinusoidal signal, and you have another time varying sinusoidal signal of different strength. Let us call it I, let us call it V. I peak, V peak. Both are sinusoids. Now, they are sinusoidal signals. Obviously, they will have some A sine omega t. Let's say this is A sine omega t, and let us call it B sine omega t, plus or minus. There is delay, right? So it after some time, t0, after some time, it started. So there is delay. Omega t means this is angle, right? So omega t0 you can tell, or I can tell it phi, because this was t0, right? T naught time. So what was the angle? Phi. Phi 0 is the omega t0. Omega t is angle, right? Frequency is omega. So t naught time. So angle is phi 0. So this is phi 0. So lag, right? This is lag. Lag means after some time it is starting. So how to represent it in phasor? Phasor plane. Because for complex numbers, you saw there was argand plane 2 plus 3i. There was argand plane, right? So 2 and 3i. So this was I, this was 2, real and imaginary. So 2 plus 3i, there was argand plane. What the argand plane did, we want either Cartesian or polar representation, where this angle and this is the magnitude, 2 square plus 3 square 5. No, sorry, this is 3 or 4, let's say. So 5, some angle theta, and theta is just by triangle, it is tan inverse 3 by 4 by 3, right? Just the angle. So but in sinusoidal signals, what can you write? Just like the complex number, we can also denote this a sin omega t to be some phasors, some reference, and b sin omega t to be some also reference. But to do so, both the signals should be of same frequency. Both signals should be of same frequency. Then only you can draw the phasor diagram, right? To draw phasor diagram. So how to quantify? We just denote, this is the peak value, right, of sine. A is the peak value. But in phasor, generally we deal with the RMS. So A by root 2. Take a reference and draw the arrow. This arrow is rotating with omega. Actually, rotation in phasor denotes oscillation in time. So rotation in phasor means oscillation in time, sinusoidal oscillation in time. Taking this as reference, because there are only two signals, taking this as reference, whose strength is A by root 2, RMS strength. Can you draw this one? Next one, which is lagging the first one? Obviously, lagging by phi naught. And assuming phi naught to be an acute angle, I can write B by root 2. B by root 2, why? Because B is the peak strength. And you know that for sinusoidal signals, the RMS strength is 1 by root 2. Up to this is clear? So now,
Yes,
this
clear.
is the phasor diagram for a lagging waveform. In time, they look like this. In phasor diagram, they look like this. And all the phasors are virtually assumed to be rotating in the phasor plane. And at any time, you can see what is their amplitude or magnitude. How? That, for example, at time t equal to t0, you see that the phasor goes here and the phasor goes here, for example. And then you can plug in, because you know already the signal. If I give you A by root 2 angle 0, this means A sin omega t. Then at time t equal to t naught, only you plug in. It becomes A sin omega t0. And easily you can find out, if you know omega, what is the value of A sin omega t0. A value is known, omega value is known, t0 is I have told you. Then you can define the strength. So you see, only by encoding the complete information of this waveform within this, I can just simplify the notation. And this also helps in the behavior of this is similar to a complex number. So that's why dealing with such phasor analysis and solving the AC circuit problems using the phasor notations and using the tools and the properties of the complex number becomes very easy. So you need to understand what I need to take as reference and how to deal with phasors, because behavior of phasors and complex numbers are all same, because you know by the Euler's representation, complex numbers can also be written as sinusoids, because e to the power j theta is nothing but cos theta plus j sin theta. So they are all actually related, right? Similarly, the sign can also be written in complex notation, but we follow the polar notation, right? So similarly, this is leading, right? This waveform is leading. This will not cut, this will cut here, right? So if I tell you this is leading, right? This leads the other one. Now it is up to you what you want to take as reference. If you want to take this as reference,
By an angle phi.
yes. So this side is leading. So B leads A by phi. And whatever notation you use for A, maybe A angle 0, so that is B angle minus phi. Sorry, plus phi. Because A is angle 0, so B leads. Leads means plus phi. And A angle 0 means A cos or sin omega t. Now for here it is sin omega t. So this is B sin omega t plus phi. Up to this it is clear, right? Let me know if you have any doubt. Now you see one thing. Sin omega t plus 90. What is it? Cos omega t. It is a minus. There is plus minus. So sin 90 plus sin omega t plus 90 is cos omega t. So if I want to encode one signal in phasor notation, if I tell if I tell sin omega t, if I want to write it as 1 angle 0, can anyone tell me how to write cos omega t? Because you know sin omega t plus 90 is cos omega t. So if I want to write sin omega t as 1 angle 0, 1 angle 0 denotes sin omega t. Then how to write cos omega t? Quickly.
1 at an angle 90 degrees.
Because cos omega t is what? Sin omega t plus 90 degree. So its signal is leading by 90 degree. So 1 angle 90 degree. Now all of you, question to all of you, okay? If I want to write 1 cos omega t as 1 angle 0. So taking 1 angle 0 as reference and sin omega t, if I called, then cos omega t would have been at 1 angle 90. Now if I want cos omega t to be at 1 angle 0, I am sitting here, okay, and looking at sin omega t. What will I see? If I take cos omega t as reference in the phasor, then where will be sin omega t?
1 at an angle minus 9.
Correct. It will lag behind by 90 degree. So from now, wherever you see sin t excitation, you can encode it in phasor representation as 1 angle minus 90 and cos t as 1 angle plus 90. Sorry, 1 angle 0. Or cos t, if you take sin t as the reference, then it will become 1 angle 0. But if you take sin t as reference, cos t will lead by 90 degree. It depends on you. If you use this, keep the convention same throughout. Don't change the convention. Because at the end of the problem, maybe you are getting some result 2 angle 45 degree. Now you want to write in sinusoidal form. What you will write? 2 cos or 2 sin? Depends on what you took at beginning. What was your convention? But always one thing, keep in mind, if you see sin omega t, then cos omega t will lead it. Because of the simple relation, right? this relation. Now you take either reference at sign and denote as 1 angle 0, then it becomes 1 angle 90. Or you take reference at here, it becomes 1 angle 0, then it becomes 1 angle minus 90. Clear?
Clear, sir.
Now I come to the concept of average and RMS. So what you know, average? This is the notation, RMS, okay? And this is average. So average is easy. For a time periodic waveform, you just take the area under curve.
Area under the
signal.
curve, right?
Yes.
Distance.
Area under the curve, mean of area under the curve, right? And its mean. Then you will get the average for a periodic waveform. Periodic waveform with fundamental period. Fundamental period means?
Time period.
Fundamental time period. T. Similarly, RMS is see from the reverse side. First square.
Root means square value.
Yes, but to do it mathematically, first you need to square, then you need to mean, then you take the root. This is RMS. But what is the fundamental idea behind average and RMS? Is the area under curve or square of the area under curve. You need to find it by graphically, and then take the area under the curve and then, or the square of the square signals area under the curve and then take the mean, and then you finally take the root to do the RMS. So you proceed in reverse direction, reverse order. First square, then mean, then root. So let's come for some examples. How to find average and RMS. Average is easy. Area under curve, half into strength, right? Half into height is I into 2t. For one, I am doing one cycle only you need to do. And then you take the average. Average is 2t. Half into base into height. Area under the curve, this is area of one cycle. Then you take the average over a complete cycle, 2t. 2t goes off. Then it is I by 2. RMS, square of this curve, how will it look? This is our parabola, right? Parabola. This is x or x square of t. This is xt. Now tell me how to determine area under parabola. Keep one trick in mind. Area under the parabola equal to 1/3. Just unlike triangle, which is half into base into height, area under parabola will be 1/3 into time period, whatever is this time, into height. Or I can write base into height. Just for the proof, see, this is slope is I by t. So what will be the equation? I by t times t dt, square it, 1 by t, integrate it from 0 to t, right? This is the area under squared signal, right? This one I am telling. For one I am telling. What will be I square by t square? T square integration is t cube by 3. Do it from 0 to t. Then you see it is coming I square by 3 into t. Correct? Yes. So you see, this parabola height was I square because it is squared signal of this signal. If this was I, then its square would be I square. So 1/3 into height is I square into base. Base was how much? You take that much duration. So up to t I am taking into 2 because area is also of the other half. For one complete cycle, I need to take the area under squared curve. So 1/3 into its peak value into duration is for one such this rising edge. And then a falling one is also there. Similar area will be there into 2. So total area I know now of the parabola. Then I square then mean. Mean is 1 over time period. 1 by 2t. And then I root it. So 2t gets cancelled and I am left with I by root 3. So the RMS becomes I by root 3. Why it became easy? Because I knew the area under the parabola. Area under parabola is simply 1/3 into its peak value of the parabola, like the triangle, the height, for the parabola, the peak value of the parabola, multiplied by the time duration of the parabola. If you do it, you get the area under that parabola. By knowing this, can you quickly do this, average and RMS? Quickly do this, okay? Because it is a repeating signal, you do for one lobe and break it down to determine the areas. Area of triangle, area of trapezium, you can use half into sum of two edges, or sum of two, I can tell, these sides into height. So average is easy. 1 by t multiplied by this much is I, or what is the this one is t by 2 and this is t. So t by 2 plus t is the 2 sum, and then half into half into I. I is the height, right, of this trapezium. So half into height into sum of two sides, which is of duration t by 2 and t, and then you get the area. And 1 by t will give you mean of that area, which is nothing but average. Clear or not? Just I will repeat again, because these are easy things you already know. So 3t by 2 into 1 by t into 1 by 2 into I is the mean or the average of this signal. T and t gets cancelled. So I am left with 3i by 4 as the average value. Can you do RMS? Just tell me total area under squared curve. If I square this curve, do piecewise. Tell me the area under squared curve up to this. Can anyone tell me? If I square this line, straight line, what will it become? It will become a parabola. Yes or no? I'm not getting any response. So what is area under parabola? Because what is RMS? RMS is area under square of that curve. So first tell me square of the curve area. So when you square this curve, straight line will become a parabola. And what is the area under parabola? 1/3 multiplied by strength of parabola or height of parabola, peak value I can tell, I square, into time duration, which is the base, like triangle, into 2, because I have also another side who also contributes to the area of the RMS, because we want to find the area under the square of that signal, into 2 plus this will be a simple rectangle, which is I square into this side into this side. So I square will be the squared one, and this will become t by 2. This is the total area, but I want to mean it because I want to find the RMS. So squared area under the curve, then mean it, and then root it. To quickly find out what it is coming. This will be t by 2, and you have t by 2 common, and I square also I take common, 1/3 plus 1 by plus 1. So 4 by 3, and you get 2 by 3, and 1 by t is also there, so t cancels. So I get whole root over 2 by 3 I square, which becomes 2 by 3 whole root over into I. This is the RMS value. Any doubt? Simply find out area under square of that curve. And after that, you mean it over one complete period and then take the root. to find out the RMS. And for average, it is simple. Area under the curve direct, and then mean it over one fundamental time period. That will give you average of that signal. Any doubt? Any doubt, you can let me know.
I square or I?
Because I square, we took the whole root over that. So I square became I. Because square, then mean, then root. Area under square of that curve, we took the area under square of that curve. Then we meaned it 1 by t. Then we completely did the square root. So the I square became I, taking it out of the square root, right? Any doubt?
So can you explain again average?
Yes, please tell me. Please be louder.
Sir, average, can you explain again?
Yeah, average is just area under this curve. Then mean it over one fundamental time period. Because what is it? 1 by t integral 0 to t xt dt. Integral 0 to t xt dt means what? Area under the curve. Because the simple definition of integration is area under the curve from 0 to t. Similarly, from 0 to t. Because 0 to t is the fundamental time period of this periodic signal. So from 0 to t, I take the area under the curve. Simply geometry. Trapezium, what is the area? Half into sum of two sides into height. So what is the sum of two sides? Half into this one. This is t by 2. Because 3t by 4 and this is t by 4. Take the difference. This distance, I can tell it is actually time, but just take the distance. This is t by 2. And this is t. So sum of two sides becomes t by 2 plus t into height. Height is I. So this is the complete area under this curve. And I mean it with one fundamental time period, which is 1 by t. And you get the area. So tt gets cancelled and then half into 3 by 2 into I. So 3i by 4. Any doubt? Kindly let me know. Because average and RMS concept should be very clear. Because after we go into power, power is always for average. But to calculate that average power, you will see we need the RMS value of voltage and current. Just we will see that proof. So average and RMS should be very clear. Like, can you tell me one thing? We write na A sine omega t. What is this A? Is this average? Is this RMS? Or is this peak? What you draw the waveform, right?
The peak value, sir.
Correct. This is the peak value. Because this is A. A sine omega t means with time the waveform is varying sinusoidally. Whose peak value is A? This is not nowhere related with average or RMS. But for this complete sinusoidal signal over one time period, average RMS means over one fundamental time period by default. So what is the average value? Just we will see in the next slide. So now I give you a signal like this, which is a half sine wave, half lobe. What is the average and RMS value of this lobe? Someone asks you. So for average, what you do? Quickly do. Average. How you do 1 by 2t and then area under the curve over one fundamental time period. But we see that from t to 2t it is not there.
0, sir.
So,
3 to 2t.
Yes. So what we can do? We can reduce the integration interval up to t. And what it means?
Vm by
Yes. Yeah, I know Vm by pi. Just let the others also just try, and you also try just deriving it. Okay. So this is area under this lobe. One lobe. This is very important. Just solve it. Sine t. I can just tell it sine t. But since this is t, capital T, I know omega is 2 pi by capital T. So sine omega t, right? Omega is 2 pi by capital T into small t. So xt, you put it sine 2 pi by capital T, because I write this as t, right? Into t, integral 0 to t dt 1 by 2t. So what is integration of sine? Minus cos 2 pi by t into t but the limit should be 0 to t. But you integrated, so you divide by 2 pi by t, right? But there is a 1 by 2t also for the average to be calculated. Now you see, minus sign, you just take it outside. So minus cos of 2 pi minus cos of 0, and there is a minus sign outside, divide by 2 pi by t, and there is a, so I take it t by 2 pi into 1 by 2t. So there is 1 by 4 pi, and there is minus of minus 2, because cos 2 pi, you take the circle, x-axis gives you cos, y-axis gives you sine. So quickly, cos 2 pi, I was here, cos 2 pi, I rotated 2 pi. So this is plus 1. Or I am doing some mistake, right? Sorry, one small error is there. This is t, this is 2t. So what should be omega? Omega should be 2 pi by 2t. It should be pi by t. Omega is nothing but 2 pi by one fundamental time period. Fundamental time period is not t, but 2t. This much. So this is pi by t. So sine pi by t. 2 should be gone. 2 gone. Okay, pi by t. And but this should be 1 by 2t, because one fundamental time period of this signal is 2t. To find the average, 1 by fundamental time period 2t. So we did that. So how, what it came? T by pi and then 1 by 2t. So this tt gets cancelled and 1 by 2 pi, and this is becoming cos of pi minus cos of 0. So cos of pi is what? I rotated pi degrees and I came to, in the complex number, I came to minus 1. So cos of pi is minus 1, and cos of 0, I am here only. So you only
Minus.
rotate in the circle and take the x-axis projection, is a unit circle. X-axis projection gives you cos and y-axis projection gives you sine. So cos of 2 pi, or what pi? Cos of pi is minus 1. This is minus 1, this is plus 1, this is plus j, this is minus j in the argand, right? So minus 1, and then 2. So 2 t by pi into 1 by 2 pi. Sorry, 1 by 2t. Tt gets cancelled, so 1 by pi. So if the strength was V, it would have become V by pi. So for a half wave sine signal, it becomes V by pi. Similarly, if we would have done a full wave, for full wave, small change would have been there, average value would have been 2V by pi. And this V is not VRMS, V peak. Similarly, this is V peak, because I told you amplitude of the sine lobe is V peak. So 2 V peak by pi for full wave symmetric. Full wave, not symmetric, full wave. Like the diode, you pass this sine and it becomes full wave. And then for half wave, it becomes Vm by pi, or V peak by pi. Two results. Now determine the RMS. Find RMS. Average we already did. Average will be 0 of this signal, right? Average of sine is 0 over one complete time period. Whatever area is on this side, this area cancels. Determine RMS for half wave and full wave, both. Full wave means, because in RMS you square, right? You RMS, you square. Square of sine is also a sinusoidal law, because sine square t is nothing but 1 minus cos 2t by 2. So this is also a shifted sinusoidal lobe, right? With frequency twice of that. Why frequency twice? Because the fundamental time period reduced by half. So frequency twice. For RMS, we need to square the signal. Now you take the area under this signal. 1. and you mean it, and then you take the root to find the RMS. So tell me RMS value for half wave and full wave. That means one is not there, like this, x square t, and then for this one, tell for both. So I do the thing for one, and I can just predict the next, because if I find the area under one sine lobe and multiply it by 2, then it will become this. But or otherwise round, if I find the area under one sine lobe, and then I can play with the time period. Either I divide by 2t or I divide by t to find the mean. Right? So just writing for half wave, this is one sine lobe area. So can you tell me what is the area of one sine lobe? Simply.
0 to pi.
No, not pi. 0 to t I am writing, right? And omega is of this sinusoidal signal. If this is t and this is 2t, omega is 2 pi by fundamental time period, which is 2t. So this is omega is pi. Yes. So sine integration of 0 to fundamental time period. So integration of 0 to t, but I want one sine lobe, right? So one sine lobe of the square of that signal. So square of that signal is sine pi by t into t whole square into dt. Because I know this signal is sine pi by t into t. How this pi by t came? Because omega is 2 pi by 2t, where 2t is the fundamental time period, FTP. You can see, na, 2t is the fundamental time period of this sinusoidal signal. So what will be omega? Omega will be 2 pi by fundamental time period is equal to pi by t, capital T. So I will plug it in here. This signal is known. Yes, tell me.
Sir, this is same for all.
Whatever is waveform you see, you first note down the fundamental time period. Yes, same for all. Because omega is always 2 pi by fundamental time period, as per definition of frequency. So sine omega t is pi by t. Now this may be t and this may be t by 2. So in that case, 2 pi by fundamental time period becomes t. But here it is 2t. So I plug in 2t. Accordingly, omega keeps changing. But the fundamental time period you need to determine what is the fundamental time period. For our case, fundamental time period is 2t. So I plugged in 2t and I get pi by t. Now sine pi by t into t whole square 0 to t gives me the area under one sine lobe. So find it, what is it coming? Sine square pi square by t square into t. Sorry. This will become what will it become? Sine square something pi by t into t. What I can write it as? 1 minus cos 2 times of that by 2. So what I can write? 1 minus cos of 2 times pi by t into t by 2. I broke it down and then integrate it from 0 to t dt. So what will be integration of half over 0 to t? It will be t by 2. And what will be integration of cos? Yes, sine, right? So sine 2 pi by t into t with the limits t to 0. But sine 0 is 0, so only plug in t. Divided by 2. So t by 2 goes out, right? T by 2 I took out because 2 was there. But there is a 2 sitting here. So minus is also here. There is a 2 in the denominator. T by 2 I already took out. So 2 multiplied by 2 pi by t, because this is 2 pi by t, right? So I am getting sine 2 pi, this is 0, right? So t by 2. into 1 by t. Now you see. So sine area under one sine lobe is t by 2. So now if I mean it over t, I am getting 1 by root 2. So for full wave, the RMS is 1 by root 2 times peak value. RMS for full wave becomes whatever is peak value, V peak by root 2. If I give you a sinusoidal signal and I want to determine the RMS, it will become 1 by root 2 times its amplitude. But what will be for half? Then you need to do 2t. The fundamental time period is twice. So it becomes half V peak by 2 for half wave RMS. So these two results are also very useful. Just I wanted to do the proof. Okay. So find RMS and average for these two signals quickly. Okay, so one more thing I want to highlight, sine t plus sine 2t plus sine 4t. What will be the fundamental time period? Fundamental time period will be LCM of T1, T2, T3. So what is the T1 for this one? T2, T3. Quickly tell me what is the fundamental time period? FTP of 1, FTP of 2, or FTP of 3. What is the FTP1 of this one? Fundamental time period of 1. Omega is 1 for first one. Omega 1 is 1. Omega 2 is how much? 2. Omega 3 is 4. So what is T1 or FTP1? FTP2, FTP3? Yes, quickly. Time period is T is 2 pi by omega, right? So 2 pi. Yes. Kindly unmute and tell which portion we were in and what you did not understand. I hope I am audible, right?
Yes, sir.
So what portion you did not understand? Don't worry, we'll take 30 minutes more, okay? No worries. So sum of sinusoidal signals of different frequencies. If it is different frequency, then it is non-sinusoidal because they are harmonics. But sum of sinusoidal signals, this is non-sinusoidal. But sum of sinusoidal signals of same frequency and different amplitude, this is a sinusoidal signal. Up to this, is it clear? If you have sinusoidal signal of different frequency, then it becomes a non-sinusoidal signal, like the harmonics, like here in this case, 4t and 2t. Both are different. But what I can comment, whatever be the waveform of the signal, even if it is non-sinusoidal because of the different frequencies, I can comment about the fundamental time period of such a signal. How? I have to take the LCM of the time period of the individual waveforms. So I know the time period is what? For the first one, this is sine t. 1 into t. Omega is 1. So FTP of 1, this sinusoidal signal is 2 pi by omega, which is nothing but 2 pi by 1, which is 2 pi. The second one, it is pi. And again, this one is 4. This one would also have been 4, right? So this is pi by 2. So LCM of pi by 2, pi and pi by 2, what is it? LCM of pi by 2, pi and pi by 2. So you know LCM of fraction is nothing but LCM of numerator divided by HCF of denominator. So LCM of numerator, what will it be? Let us suppose it is pi by 1. So pi by 2 and pi by 1 LCM. What is it? LCM of numerator is pi and HCF of denominator. So you see the larger one is becoming the LCM or the time period of the overall signal. So from this I commented two things, that sum of different frequencies of sinusoidal signals is a non-sinusoidal signal, okay, but its fundamental time period of the overall signal can be commented, and that is nothing but LCM of the time period of individual sinusoidal signals. And we know that sum of sinusoidal signals is a sinusoid if they are of the same frequency. However, they may be of different amplitude. So that's the result. And the LCM tells us that the fundamental time period of this overall signal becomes what? Is nothing but pi. And it is a DC offset is there, 4, average value. So I told you when you take the average, you integrate from 0 to fundamental time period, which is pi, of the overall signal, you get all these terms to be 0. Because integration of our fundamental time period of any sinusoidal signal, because they are all within this time period, right? Fundamental time period means all signals are within that time period because we took the LCM. So all will become 0 because you know average over one time period sign is 0. So average will only be 4, right? That average value. And similarly this one for 2, average will be 4. Now tell me RMS. For RMS it is easy. RMS is nothing but root over average square plus half of sine strengths. V peak 1 square plus V peak 2 square. Like sinusoidal signals are there. Or you can tell average value square plus VRMS 1 square plus VRMS 2 square, likewise, whole root. It is nothing but square of the RMS strengths of different individual quantities. So for 4, the average or RMS are same. It is 4. So 4 square plus, what is this? 2. 2 means its RMS is 2 by root 2 whole square. You see 2 square, peak square divided by 2. So that's why I took a half common. So you take a half common and then square over all the peak values of the sine. Now you can add two same sines. Sine 40 and sine 40 can be added. So 2 sine 40 plus 8 sine 40. I can write this as 4 plus 10 sine 40 plus 6 sine 6 cos 2t. Cos sine does not matter in RMS. Only you need to take what you see, 4 square plus 100 plus 36. I squared both the signal and took a half. Then whole root over.
2
Whatever.
sin, sir.
Yes, tell me.
2 sin. Yes,
Why
okay.
the 2? Because the RMS of one sine signal with V peak as the amplitude is V peak by root 2. That's why 2. Because we are squaring the RMS. So when square the root 2, then it becomes 2. That's why a 2 is common. Half. So what I told you, RMS of such signals, which is a sum of many sine signals of different frequency, is nothing but individual sum of RMS squared of the signals. So I square. So if I know the RMS of first signal, 2 sine 4t, what is the RMS of 2 sine 4t? It is 2 by root 2. So square it, then add it with the next one. Next one is of a different frequency, cos 2t. Doesn't matter cos or sine, but I have to take the RMS value. What is that? 6 by root 2. Because peak strength by root 2 is the RMS value of the next signal. Square it, add it with the RMS value of the next signal. What is it? 10. So 10 by root 2. 10 is the peak value of the different frequency signal by root 2 square. Then this is non-sinusoidal. So 4. Average RMS are same. 4 square. Whole root over. So since there is a by root 2 in all the sinusoidal signals of different frequencies, so we took the half common and then squared the different strengths, peak values, and then added it and whole root over it. So that is how you determine RMS of a signal which is periodic but of a addition of many sinusoidal signals. That is how you do it. So you try, you will understand. Okay, so this is the basic relation. RMS is nothing but average of the average value, the constant value I can tell, whole square plus half of individual sinusoidal signal of different frequencies. So these are all different frequency. Even if you take same frequency, it will add up. So nothing, no worries, right? Because and 1/2 came because of the 1/√2 phenomenon. Because the RMS value of individual sign is peak value by √2. Then you whole square and then add with another sign of different frequency, whole square by √2, which becomes half, and then take the half common and then sum of the square of the peak values. Right? You do once this example and then you will understand what I'm trying to tell, right? Do it yourself, okay? So the RMS value of the next one will be how much? 4 square plus 2/√2 whole square plus 6/√2 whole square. Either you take half common and square the peak values, or by √2 you individually sum of the RMS values and whole root over. Right? You try it, and the phase shift doesn't matter, doesn't contribute in the RMS value. You are seeing neither the frequency nor the phase shift is contributing anything in the RMS value. Only this amplitude of different frequencies of sinusoidal cos or sine anything will contribute, right? And also be careful, if someone asks you, is this a sinusoidal signal or a non-sinusoidal signal? Obviously, this is a non-sinusoidal signal because there is different frequencies of sinusoids, and different frequency of sinusoidal signals cannot add up to a sinusoidal signal. Okay? If they are same frequency sinusoidal signal, then their addition will be sinusoid, right? Even of different strength also. Then also that will be a sinusoid. So they are just try these things. These are very fundamental things and should be known, right? I thought to cover all these things. So peak factor and form factor, very easy. Peak factor is nothing but, anyone knows peak factor? I will just quickly write it down for you. So if I write peak factor, you, as per the term, you know peak factor is what? Peak value divided by RMS value. So
maximum one alternating quantity.
Yes. So peak value is nothing but its peak value is V, and RMS value of sinusoid what? V by √2. So this is nothing but √2. So peak value of this sinusoidal signal is √2. Peak factor is √2. So simple, right? Why it is used? To define the rating of fuses and other things. Fuse, right? How much fuse you will choose in the circuit to determine that. And form factor is what? Form factor is nothing but RMS by average of the signal. But you know the average value of sinusoidal signal is 0. So it is coming infinity, but not so. So in order to not turn it infinity, we do one lobe. One lobe, right? One lobe symmetry. So for one lobe, we take the average. Average only for one lobe, okay? But the RMS to be done for the whole. So RMS of sinusoid is nothing but V by √2. Simply you write it down. Average. Average, since it is coming 0 for the complete, you do for 1. Okay? And what is average of 1? That is a mod of the signal, right? One lobe symmetric mod V. Average over mod V you do. So what is that? This like this. So that you have to average over one lobe. So it comes 2V by pi, as we already saw for the full wave first. For half wave symmetric waveforms, half wave symmetric means this one and this one are negation of each other in the half cycle. If you just shift, yes. If you shift by t by 2, that will become minus of that. X t by 2, t plus t by 2 is minus x of t. Half wave symmetric waveforms, since it's cancelling and becoming 0, to not make it 0, we take average over mod of that signal, which reduces one lobe. So you take one lobe and 2V by pi it will come. So it becomes 1.11. That is the form factor. Okay. You just see that it will become pi by 2 root 2. It becomes 1.11. These are all very trivial things. So now let us jump into the phasor diagram. I already told you. Phasor diagram I'm not covering again because I already told you it earlier that it is behavior is same as the complex number and you have to choose the reference point very correctly. And it will be clear once we solve the problem. So let us jump into the problems because we are already late and want to take 30 minutes more to finish the problems, right? So let us start the problems. Okay. So series and parallel RL circuits all are same. Just to stress upon the problems, I would like to just cover it. So you see series RL circuits, you know that you have AC and you then have R and L, right? But I already told you that if it is Vm sin omega t, the voltage you are giving, then this omega will determine how much is XL. So there are terms like impedance and reactance and resistance. Resistance is same in DC, is R. Reactance is the impedance offered by the L. It's called reactance. It is omega L. And however, it has a plus J with it. Why plus J? Because you know if the voltage is V, the current through the inductor lags by 90 degree. So that's why there is a minus 90 degree and one angle 90 is J. If you multiply or use J in the argon plane, you see J is here. So it is one angle 90 degree, the notation. So V by I angle minus 90 becomes V angle 0 by I angle. If I take the reference at V, you see, then I am getting V by I angle plus 90 degree. That's why the plus J sign with the inductor. And why the inductive reactance is J omega L? Because you know V equal to L di dt. So V of S, if I take the Laplace, L into I of S into S, you know di dt, d dt, it becomes J omega, right? So S will become J omega because SIS, right? SIS. It di dt becomes SIS. So you put V by I, you get inductive reactance. And inductive reactance you get from the formula as SL. And S I can write J omega L. So that's why the plus J. And I will lag behind by 90 degree. Why? Because V by admittance reactance is nothing but XL has a phase and amplitude. So one angle plus 90 degree because of the J I told you, and V angle 0. So that's why I angle minus 90 degree. V by some XL mod, some strength, omega L has some value. So you see I lags by 90 degree. Anyway around you can just flip it and show the other one, that the inductor current lags by 90 degree. But generally speaking, for a series circuit work with current as reference. Because why? Because current is same through all elements. And for parallel circuit, what will happen? Can anyone tell me? Take
Voltage is a reference.
voltage as reference. Because voltage across all elements or most of the elements are same. Now why to do? Because easily you can do angle 0. Reference means angle 0. V angle 0. Vm sin omega t. Need not write so much. But for series circuit, I needs to be taken as reference. the current. So that is the thing. And this is the parallel RL circuit. Same. And it is easier to work with impedance in series circuits. However, it is easier because you took current as reference. And it is easier to work with admittance in parallel RL circuits, because they are the addition and of different impedances. The addition becomes very easy with admittance because the reciprocal is happening, right, in parallel. So these are some very minute things which will simplify your problem solving skills, right, and make it easier. So just maybe just keep this in mind. Okay, so for series RL circuit, you do the current as reference, and once you take the current as reference, just tell me what will happen if I take the current I angle 0. I don't know how much is I, but I know V. So what will be V? Can anyone tell me what will be V from phasor diagram? Let me do another new slide. Yes. So can anyone tell me? But because now your problem solving will come, idea will come from this one. If I take I as reference, I angle 0. So what will be voltage across the resistor and voltage across the inductor in phasor sense? Can anyone tell me? VR is I into R. The strength of VR, amplitude of VR, and its direction is inline to I. Agreed or not? I into R, simply. It does not add or change any phase. The R does not have any phase, right? Similarly, I times j omega L, I times j omega, whatever is I is the reference. I times j omega L. Whenever you multiply any phasor with j, it rotates by 90 degree in the clockwise direction, in the clockwise direction, right? Anti-clockwise direction. Plus j, because you can verify. Plus j means anti-clockwise, right? One angle 90 degree. Anti-clockwise is taken positive, right? So you multiply by plus j, then the phasor rotates by 90 degree. However, it is not only plus j, but plus j times omega L, and then multiplied by I. And when you multiply phasors, then angle gets added. Otherwise, multiplication of sinusoidal signals will have been difficult, but in phasor it is easy. When you multiply, phasors get added. When you divide phasors, angle gets subtracted. And whenever division comes, you can just subtract the angle, and the magnitude gets divided as usual. So what was the amplitude? Plus j means one angle 90 degree rotation. But the amplitude or the magnitude would have been omega L times I, mod I. This would have been the amplitude, right? Angle VL. So you saw VL is ahead by 90 degree with VR. And VL, by Kirchhoff's law, V is VL plus VR. But not in the scalar, but in phasor sense. So apply your vector skills. So this will be V, angle theta. And theta is nothing but tan inverse VL by VR. Now VL and VR are what? VL is mod VL by mod VR, triangle, right? Amplitude. So j omega L into I, mod I can write, and mod of whole thing J will go away. So I omega L and IR. So I gets cancelled, mod I can write. So tan inverse omega L by R. So this theta is nothing but tan inverse omega L by R. And what will be the power? Power is I RMS square into R. Why? Because power is nothing but V R into IR. So what is it? IR is V by R. So V square by VR square by R, or IR RMS square into R. This is the average power, right? Or if you want to write in apparent sense, S, it is Vs into Is. I already know, I angle 0. Vi know, V angle theta. Now S is Vi conjugate, right? Because why conjugate? Because you want to find the difference between the two. If V is at an angle theta and I is at an angle, let's say V is at an angle theta 1, I is at an angle theta 2, power will be V into I RMS, let's say. And the difference of the angle between the two, that's why I conjugate. Angle between V and I. If you would have multiplied V and I phasors, the angle would have added. But I don't want that. I want the angle between the two. That's why VI conjugate. V phasor into I phasor conjugate. So V phasor into I phasor conjugate is nothing but V angle theta, because current is taken as reference and I saw voltage leads by the phasor diagram. So VI angle theta, I conjugate is nothing but same, and VI angle theta. S is VI angle theta. And what is that? VRMS into IRMS angle theta. Because when you do the V sine T and maybe I sine T, and their peak values, and then maybe integrate over 0 to t 1 by t, you will find that Vm by 2 into Im by 2 it will come. So that's why I'm writing Vrms into IRMS. And a cos of theta will come. Theta is the angle between V and I. So that's why I wrote Vrms into IRMS angle theta. And P is nothing but IRMS square into R. Because the real part of this is known as apparent power. And this is known as active power. And the reactive power is nothing but IRMS square into XL, because there is inductor, or XL minus XC, whatever is more, or VRMS, IRMS, sine theta. Now, why cos theta, sine theta, all these things are going? Because according to if this is V, if this is I, V into I is power, because I assume no phase lag, right? So how the active power will look? With twice the frequency. However, reactive power, how it looks? Just see. V is like this. You shift it by 90 degree, because I know that V and I shifted completely by 90 degree will contribute to reactive power. So you shift it by 90 degree, right? Then it becomes, if you multiply these two, if you multiply sine t and cos t, what will it be? It will be half sine 2t. And this is nothing but reactive power. Because completely average over one fundamental cycle is 0. So reactive power flows in one direction in one cycle and returns in one direction in the other cycle. That's why it does not contribute to any power over one average cycle. That's why we say that reactive power is unaccountable power. It comes and goes away and does not contribute to any net average power, right? That is the basic philosophy why it is happening so. So now you do this one, angle between Vs and VL, what will it be? We already talked about these two things. So as per the phasor diagram, always draw the phasor diagram. This is current taken as reference because of the series RL circuit. And you know, I times R is I times 1 mod I. I don't know what is I. I need not find also, because only the angle between VS and VL are being asked. And then this is VR and direction is shown. Now VL is I times J root 3. Now since there is a plus J, the complete thing will rotate by 90 degree. I times J root 3 means wherever I was, I will rotate by 90 degree plus 90 degree and into root 3 because of the J omega L. So J root 3, and this will contribute to VS. Now VS and VL, this is VL, mod VL, and this is VS. So this angle is being asked. Can you tell me what is the angle? So tan inverse this length by this length. So this length is nothing but mod I times 1 divided by mod I times J root 3. I gets cancelled and we get, so mod of whole thing, so J will go away. So tan inverse 1 by root 3 is nothing but how much? 30 degree. Coming to the next problem, you know the angle between these two voltages are 90 degree. Just I showed you VR and VL. Because of simple I times J omega L. VL goes 90 degree leading to VR. So these are all 90 degree to each other. So I know by Kirchhoff's rule, they are addition but the phasor addition. So phasor addition of two quadrature voltages is nothing but by Pythagoras theorem. VR and VL, they are quadrature. So they are the total voltage magnitude. So Vs magnitude I can write is square of the 2 and then root over. And what will it be? 20. Hope you are getting it right. Just draw the phasor diagram, everything will be clear. So how to determine V2 and V3? They are already, their values are given, right? And they just assume these are the RMS values, right? These are all the RMS values. So phi L is the angle between V2 and V3. So how to draw the phasor diagram, right? Take the I as reference and then I into R2 is V2. Then I into JXL, this is V3. And then you add I into RL because I is taken as the reference, right? So this becomes our V3 total. JIXL plus IRL. This total thing is V3. So this is V3, this is V2. So this is phi L. Now how to determine phi L? Phi L determination is easy because you already know V2 and V3 and V1. So I know the phasor diagram, right? See, V2, V3 and their summation is V1. So what does parallelogram law say? V2 square plus V3 square plus 2 V2 V3 cos of angle between V2 and V3, which I call as phi, whole root over will give me what? The amplitude of V1 by parallelogram law. By phasor diagram also you can see. So this is phi L. When you solve this thing, because V2 known, V3 known, V1 known, all are given. When you plug in the value, you will find out that cos of, I'll just write, is 0.45. So you find phi L from there, right? It is phi L is cos inverse 0.45. Then the voltage across RL, this one, what will it be? Voltage across RL is what? From the phasor diagram, can you say? Voltage across RL? Yes, V3 cos phi L is VRL and V3 sin phi L is VL. This much. VRL and VL. Why? Because you see IR2, this is V2. Then I times JXL. Then add it with IRL. This addition gave you V3. So V3 and this angle was phi or theta. So this angle was theta. So V3 angle into cos theta, this arm would give you VRL and V3 into sin theta will give you VXL. Hope you get it right. I'm not delving more. Just by geometry it comes, okay? So it comes as 61.57 and this will come out as 121.17. Just plug in the values, you will get it, okay? Because V3 is known and cos phi L is known, then sin phi L also known. 1 minus cos phi L whole square root over. You get these values, right? Accordingly, you do it, okay? So now just go to series and parallel RC circuits. Now we saw how to deal with RL circuits. Now just go to RC circuits, right? So how to go with RC circuits? RC circuit, you see, same. For series, always remember for series, current as reference, for parallel, voltage as reference. So these are, this is C, and then this yes, VR plus VC is nothing but supply voltage in phasor sense. Don't add it scalar wise, right? Because phasor directions matter. So similarly, current as reference, I as reference, IR. But I, you see, it is minus J by omega C, XC. Like unlike XL, it is minus J by omega C. So it is lagging because I told you minus J means one angle minus 90 degree. So XC into IL, I is nothing but VC and this is VR. So VC plus VR is nothing but net V. So net V, if I taken the reference, net V lags. In other words, I leads the voltage in case of capacitive circuits. Just that much I want to tell you. Similarly, you can write I into Z, which is nothing but I into R plus I into, because I is the reference, I angle 0, R angle 0, I angle 0 into minus J by omega C. So minus J by omega C. And I know minus J means 90 degree, minus 90 degree. So I gets cancelled and Z is nothing but R minus J by omega C. Similarly, in case of inductive, R plus J omega L. So remember these things. So in case of series circuits, current as reference, I as reference, and work with impedances, resistances, and reactance. For parallel, what we do, V, R, C, and this is IR if I call, correct, voltage as reference. So what we do, this is net I by KCL, IR plus IC. What is IR? V by Z. All are having in phasor sense. V by R plus V by minus J by omega C. Now when you solve, V gets cancelled because voltage as reference. V angle 0, or V, both same. So comes J omega if you do it. Okay. So us in indicates the susceptance, right? Noted as BC. Susceptance, right? Inverse of, it is not exactly the inverse of reactance. Please be cautious. 1 by Z is known as what? admittance. See, one important thing I want to highlight. Admittance is inverse of impedance. But susceptance is not. Because this is complete inverse of 1 by z, and then whatever comes, we call it susceptance. Similarly, 1 by r is conductance. So these two parts are not exactly the inverse of these parts, r and j by omega. Hope you understand. Complete inverse of z is giving me after admittance is inverse of impedance. So G is plus, then it just remember equal to plus J plus, then it is inductance. So admittance I to G plus is plus
Sir, what is susceptance?
capacitive. Is plus. Yes.
Sir, what
Can I
is
tell
susceptance?
you? The real part is sorry, imaginary part of admittance. V is imaginary part of the capacitive, and if it is the circuit is inductive. Similarly, reactance is the imaginary part of impedance. If it is positive, the circuit is inductive. If it is negative, circuit is capacitive. Okay. Just don't remember this term. But probably don't everything. Just terminologies. Okay. So now I hope the screen is visible, right?
Yes.
Go to the next one, next problem. So I 10 more, right? So this problem to this is simple. This is J1 you need not write 1 minus J, okay? And mod Z is nothing but, so if you want to write it in phasor notation, what will you write? Root over 1 square plus 1 square from Cartesian to polar, just like that in complex number. Tan inverse minus 1 minus angle minus 45 degree by triangle law. Okay? Root 2 angle minus 45 degree. And R of t is nothing but V by Z. Now V is cos omega t. Cos can be taken as angle 0, 1 angle 0. So 2 angle 0 by root 2 angle 45 degree. So I took cos as the reference. So 2 by root 2 means root 2 angle 45 degree. So how to write? Since I took cos as the reference. So this is the peak value, right? And I need to convert everything into RMS. So 2 by root 2 I need to write. While polar notation, all in RMS. If you take all in peak, take all in peak. Okay. So I took all in RMS. So 2 by root 2 angle 0 RMS divided by root 2. So it will be 1, right? 1 angle 45 degree. So it will be coming cos of E plus 45. Because it is 45 leading and I took cos t as the reference. So 45 addition to that because it is plus 45. And because this is RMS, this will have been also been RMS. Because what is current? Current is V RMS by Z. Or if current peak value is needed, V peak by Z, then it will give you peak. But I want RMS, right? But this is giving me RMS. 1 angle 45. So again, when I write cos, I need to convert to peak. So root. So either you take everything in RMS or you write, convert everything into peak and then solve. But don't forget that when you write A sin omega t, A is the peak value. So since I did all calculation in RMS, while writing it again in sinusoidal form, I need to multiply again root 2 because I need to write in terms of peak. Right. So that was the thing. And IT I found out, and then VR and VC. So this was I, this was IR, this is VR, and VC is nothing but lagging, right? I into pi omega c. VR and VC, how to write? This is V. So I times R is nothing but VR. I times I by omega c, I times XC is nothing but VC. So I, if you need root cos will give me, so it will cos plus 45. Right? This is RMS, and this when right it is peak. And I by omega c, omega is 1, then 1 by c, c is also 1. So similarly it will be root 2 cos t plus 45. Same, because both are 1. And power, P and Q. Power will be nothing but I RMS squared into R, and Q will be I RMS squared into XC. I told you. Then I RMS is known, it is 1. 1 into 1, it is 1 watt. And it is also 1 watt, volt ampere reactive. Apparent power, if they ask, it will be root 2 kVAR. Because what is apparent power? It is root over P square plus Q square. Both are 1. So that's why it should be like that. Definition of power, I told you. But let us, definition of power is nothing but it is V of T into I of T and then 1 by T. It is average over one cycle, right? Power always average. Right? But you see the formula of power, it always comes with RMS. Average power is denoted by product of RMS values of voltage and current. Similarly, active power, if you tell the RMS, IRMS, cos of angle between the two, and then this is sine of angle between the two. This is simple, right? And I told you how the power looks like with double frequency. This is the power waveform. The active power waveform, frequency is 2 times, then voltage and current, and then this is the reactive power waveform. It comes and goes away, and the addition of 2 will give you the S. And but all we denote with average. But since Q average is 0, we take again the mod of this signal and then do the average. Because otherwise it would have been 0. But Q average I wrote as VRMS, IRMS, sine theta. It is nothing but mod of Q and then taken the average. Over one cycle, we will give you VRMS, IRMS, sine theta, right? It is because otherwise it will be 0. But it is, if it is 0, we cannot quantify the reactive power. Because otherwise the addition of the two in phasor sense will not give me the total power. And just speaking in terms of direction, since V into I, if in both in same direction gives me power, active power, contributes to active power, we actually denote the active power as V into I both in same direction, or component of I in line with V. So active power is, if it is taken like this, reactive power is actually in quadrature with active power. Why so? Because either for I leading by 90 degree or I lagging by 90 degree. So that's why if V is the reference and I angle 90 or plus minus 90, then we get Q to be plus minus 90. So actually plus minus comes if it is P plus JQ, then I tell that circuit actually absorbs the active power. P minus JQ it delivers. So it is capacitive and it is inductive. We form the power triangle. And this is S. Because V times I angle plus angle 90 degree conjugate is S. And if I is leading by 90 degree, then it is capacitive. So it becomes P minus JQ because there is a conjugate. Similarly, if S is V times I angle minus 90 degree, which is for inductive, but there is a conjugate here, so we get P plus JQ form. So it is inductive. This kind of absorbs reactive power, and this kind of I can tell delivers Q. But those are fictitious terms since Q is neither absorbed nor delivered, because in one cycle it comes and other cycle it goes in the instantaneous sense. So concept of power triangle I told. So from the power triangle only I RMS square into R and I RMS square into XC or I RMS square into XL, I can form the power triangles, right? And then from the power triangles, I can draw the impedance triangles like R, XL, XC, and Z. So both works, right, to determine the power factor angle or the angle between various quantities. So as I told that if given two signals 60 cos omega t and 1.5 cos omega t, both are of the same frequency, otherwise they will not contribute to power, neither active power nor reactive power. So since they are of the same frequency, the product of the two will give me apparent power, the product of the RMS of the two, right? So the S is nothing but 60 into 1.5 by 2. 60 by root 2, 1.5 by root 2. So 60 into 1.5 by 2. And just writing it down for your reference, it will be 45 volt ampere. The real power or the active power is nothing but, so real part of apparent power is nothing but active power. So it is nothing but active power. And imaginary of S, I can term as reactive power. So P can be denoted as, I can write it as VRMS into IRMS into cos of angle between two, which is nothing but 60 degree. So I get 60 into 1.5 by 2 into cos of 60 degree, which is half. So 60 into 1.5 by 4, which is coming as 22.5. Just check once again, okay? And then Q is coming as simply sine of 60. So it comes as 60 into 1.5 by 2 into sine of 60 degree. This is nothing but root 3 by 2. This is nothing but 38.97. And then from there, we can determine the power factor. So power factor is cos of angle between two. So if voltage is like this, current is actually leading by 60 degree. So cos 60 lead. So never write power factor as only one quantity. It should be written that whether lag or lead. Okay. So cos 60 degree lead. And accordingly, load impedance can be denoted as Z equal to V by I with phasor notation. Then it can be denoted as 60 angle minus 10 divided by 1.5 angle. So if you take in peak, take in peak. If you take in RMS, take in RMS. Okay. Yes. So it is coming actually capacitative, right? Because it is leading. Capacitative as Z has negative imaginary part. So I get it as. So I am writing the answer 20 minus J20 root 3. So nature of load is capacitative since it is leading, current is leading. And it is a simple problem. Find P, Q, and S for source and load. If this is load, so V angle 0 by Z net 2, and you find I net, I, and then I RMS squared into RS will give you PS, that is this impedance, the power dissipated, and then I RMS square into XS will give you QS, I RMS square into RL will give you PL, I RMS square into XL will give you QL. And the values I am writing it. The current will get as 2 angle minus 36.86 degree, and then PS will be 4 watts, QS will be 8 watts because 2 square into 2 is 2, and then the load impedance is 2 square into 7, and I get 28 watts because I get the power, right? Power unit is watts, but apparent power unit is volt ampere, but the reactive power unit is volt ampere reactive. So this is volt ampere reactive. Similarly, this is also QL is becoming 16 volt ampere reactive. So coming to that, these are simple problems. So I told you for similar frequency only, it will contribute to power. 2T, it will contribute power. This will not contribute power because there is a 4T. There is no 4T. So no. Because 5 10 root 5 by root 2 RMS of voltage into RMS of current multiplied by cos of angle between two for this frequency, and then summation of this one. This one will not contribute to any power. So 0. So total power that you will get for this system is 120. So for active you take cos, for reactive you take sine. Active it will get 100 watts. Reactive only replace cos by sine. Other is same, right? So it will get 125 watt. You will get 125 square plus 100 square whole root over. Whatever is coming, that will be S. So it asks to find power factor lead and 0.8 power factor lag. Overall circuit. Overall circuit means it is asking about the source power factor. Okay. So your since this is a parallel circuit, you deal with the admittance, right? So 1 by 1, and this is 1 plus J1. So 1 by 1 plus J1 plus 1 by XC. That will be Y. 1 by with a j. So 1 by 1 plus j1 plus j1. So jc. So we get by reducing it as c minus half. So I told you if this is plus, it is capacitive. If imaginary part of y is positive. So it is leading, if it is 0.8 power factor leading, so tan inverse c minus half by half would be, and another case will come. So cos of tan inverse, this is 0.8, one case, and then one more thing we can do, cos inverse 0.8, which is 36.86. This is the angle. So tan inverse c by will be positive, and this for lead, and tan inverse c minus half by half, this will be minus 36.86 for lead. Accordingly, it will give me two values, and from there we can determine c values, right? And there is a simple problem which asks me to find out V2 by V1, and it will be simply V2 by V1 is a series circuit, so I as reference, and then I get this simply boils down to Z2 by Z1. I is same, and Z2 by Z1 I do, then I get 5 minus J12 by 4 plus J3, because this is 1 by omega c and this is omega L, and omega is 3, right? And there is a sign minus J and plus J. So you do that, and they would do that, take the mod, and then it give 13 by 5. So going to the next problem. You see that the steady state output of the circuit is given as A sine omega t plus 5, and A is given to be 0.25. So this voltage amplitude is given as 0.25. So output frequency of the circuit is being asked. Or the forcing function is having a frequency of omega, but the omega is being asked. So accordingly, we need to analyze the problem, right? So what we do, we actually know this voltage drop as 0.25, and because the symmetry, we judge that the 0.25 voltage drop magnitude wise occurs across the other capacitor. So this voltage total amplitude becomes. So now if we can calculate the voltage drop across this total part and equate it with 0.5, its modulus, then only we can determine the, by voltage division rule, then only we can determine the frequency omega, because we know the one part amplitude. C and this C are in series, which gets it C by 2, and C by 2 parallel with C will add it to 3C by 2. And the voltage across 3C by 2 is 0.5 voltage amplitude. So V across 3C by 2 amplitude, if I equate it to 0.5, I can get the frequency. And this will be done by voltage division rule. And voltage division rule will be 1 sine omega t, or I can write 1 angle 0, taking sine as the reference, multiplied by the impedance J by omega c. Omega is like this, and divided by R plus J by omega c, because I want to take the mod, right? But there will be a minus sign. And top it doesn't matter, but bottom minus sign matters, right? So just do as homework. We'll just specify the answers. So this is 24 angle 0 by 6. If you do the Z total, you will get Z total as 2 plus J2 in parallel with minus J4, which comes out as 6 ohm. So unity power factor, right? Because Z total appears to be simply a resistance, it will come out 4 angle 0 ampere. So I1 you will get as 4 angle 0 by current division rule into minus J4 to the other branch divided by total impedance. It will then give you I1. 4. Similarly, Q across 1 by 8 farad and P across, so Q across 1 by 8 farad, it will be I2 RMS square into 1 by omega C. Omega is 3 and C is 1 by 8. Accordingly, you will be able to calculate all the elements P and Q, right? So, sorry, this will be 2. So 4 into 4 square. It will come out as 64 bar. And 4 45 degree. Yes. So just writing it, I1 and I2 in phasor form, 4 angle 90 degree, and I1 will be 4 root 2 angle minus 45 degree. So just coming to the last problem, it is asking to calculate I of t through this branch. So just you can apply KCL and just do 2 sin t. So I told cos we just took as sin we can minus 90 degree x cos. So 2 will correspond angle minus 90 degree. V minus 2 angle minus 90 degree by j. So 290 degree can also be minus plus I of t plus minus 2 minus 90 degree. So this is minus j, this is plus j. So V minus 2 angle minus 90 degree by minus j, this current, and this is the current that the capacitor gets. This current goes into this source, and by Kirchhoff's current rule, sum of these three currents will be 0. And then we get by solving get as 2 angle minus 40. So this is RMS. So assume P, right? Assume P, answer will come. So now root 2, we assume omega E minus 45. Plus theta cos theta and theta plus 90, yes, angle with t minus 45. It multiplied by is root 2 45 degree. Okay. So you know V, find out I as 2 t minus t plus 45 degree because it is 1, right? So this we end the session and I think in okay. So now I think the screen is visible. So the last part just missed out because of the network issue. So this was the nodal equation, and then writing it with the KCL, we equated it to find the V. And once we found out the node voltage divided by the resistance value will give me the current through that branch. And it is simple. Just if you assume the voltage in the magnitude peak amplitude form, then the answer will come in peak amplitude form and you don't need to multiply root 2. And you can directly write from polar form to the time domain form in cos, because we assumed cos has the 1 angle 0. And then sine we accordingly 1 minus 90. But while from polar to cos, we abide by that assumption. The actual phasor notation of the reference and these are two Cartesian number. The advantage of using complex number similar calculation. Using addition and subtraction. So addition Cartesian form is multiplication. Because numbers, right? That's why that said about multiply and then they have the from Cartesian. And the complete numbers. How you using the calculation, the transformation, the repeat. So that is how you use the IIT state response. This is useful. That is all for this. We close and you for joining the